factoring polynomials. So last time we talked about what a polynomial was, right? And I would encourage you, to read through my catalog of elementary functions, right? We talked about like sine, cosine, exponential, logarithms, all that stuff in chapter 1. So I didn't really write all that up on the board, but I would encourage you to read through there. We'll be coming back to those functions as we go on and study calculus. We'll study how to differentiate something, and then we'll start looking at examples of how to differentiate the different kinds of functions like sine and cosine and so forth. So we will come back to those functions as we go on. But let's see here. So basically, the big theorem that I shared with you guys last time was the factor theorem, right? Which is if C is a real number and P of X a polynomial, right? Then P of X is equal to X minus C times F of X, if and only if P of C is equal to 0. All right? So this is the factor theorem. And let's see, we did in class example 1.67 and 1.68. And we were just getting to these three in-class examples on page 41. But this is the big theorem from last time. I suppose I should probably give you an example of this. Let's see here. So this one's not in this one doesn't really fit in the notes. I'm just adding an example. All right. P of X equal to x cubed plus 13x squared minus 11x, all right, minus 3, all right? Let's factor this. And I'll give us a hint. 0 and 1 might be interesting. So I'm essentially I'm adding one example to page 41 before we go on. That's what I'm doing right now. Okay, so I said might be interesting. Well, what happens if you look at P of 0? What's P of 0? We've got 0 cubed plus 13 times 0 squared minus 11 times 0 minus 3, which is what? Well, that's minus 3. So that's no help. It's not 0. Factor theorem doesn't help us out at all here, right? How about P of 1, though? We get 1 plus 13 minus 11 minus 3. So that's 14 minus 14. That's 0. So what does that say? That says that x minus 1 is factor, right, of P of x. Now, how should you factor out x minus 1 from this cubic? There are two strategies I would use. All right, two strategies. So let me show you the first strategy. The first strategy thinking. Thinking. All right, so thinking, I mean, write down what has to happen. P of x is x minus 1, right? That's a factor in it by the factor theorem. Times something, right? I'll write down here, P of x is, what was it? It was, I'm just writing it here so it's closer. X to the third plus 13x squared minus 11x minus 3, right? So, thinking. What has to go here? Has to be quadratic, right? Right? It has to be something of the form ax squared plus bx plus c, right? But can you tell me, well, think about it. When we multiply this out, right? When we multiply this out, we have to get back that x cubed, right? So think about it for a second. What do you have to put here? If this times x squared, right, returns this x cubed. So clearly I can put a equals to 1 because I have to multiply this back to get the x cubed. All right? Now, what else? How about this constant term, this minus 3? Where's that coming from? That's coming from the product of the constant term in this factor times the constant term in that factor. That's the only way we can get a constant from the product. So whatever number I put over here, it has to be whatever number I need times minus 1 to give me minus 3. That forces me to write what? 3. So I can say plus 3 over here, right? So now I get to the middle. What do I have to put there? Now there it's a little bit trickier, right? Yeah, what I got to put something with x there, right? And so if I put plus bx here, right? For a second, what does that give you? That gives you bx squared, right? But minus x squared. So the only way to get x squared is from this times this, and this times that, right? So that gives me b minus 1 x squareds from this product. So b minus 1 has to be equal to 13. That forces me to put a 14 here. And then you can check it. So 14 times minus 1 gives me minus 14x plus 3x. Minus 14 plus 3 gives me that minus 11x. Checks. This is actually a pretty fast method for factoring a cubic if you already know a linear factor, once you understand what you're doing. Because the blue term and the orange term are essentially for free. It's only the middle one that you really have to ponder. Now you're like, well, I'm really not enjoying what we're doing. This doesn't seem like a good path. Well, here's strategy 2. Strategy 2. Long division. So what we do is we take our x cubed plus 13x squared minus 11x minus 3, and we just divide this x minus 1 up in there. See what happens. Right, so I get myself a x squared. That brings down x cubed minus x squared, which brings me to 14x squared minus 11x minus 3. Right? And okay, so then I've got a 14x squared I got to get rid of. So I would do, like what, plus 14x, right? So that gives me 14x squared minus 14x, which is going to give me 3x minus 3, right? So then I say plus 3. That gives me 3x minus 3. The remainder is 0, which is good. Right? So thus, by long division, x cubed plus 13x squared minus 11x minus 3 is equal to x minus 1 times x squared plus 14x plus 3. So there's two different strategies for how we can factor a cubic if we know a particular linear factor has to factor out, right? Now, fun fact, every cubic has a linear factor, right? Because if you think about the graph of a cubic, it has to be basically, big picture of a cubic is it's either kind of like this or it's kind of like that, right? Oops. That. Oops. That. All right, so anyway, the point is the cubic either goes from minus infinity to infinity or it goes from infinity to minus infinity as you read the graph left to right, right? So there has to be some point by continuity where that cubic's graph crosses the x-axis, right? There has to be some point where there's a 0 for a cubic polynomial, which means we can always factor out x minus c for some choice of c. It might not be pretty, in general. And finding the place where it crosses is generally a problem of numerical methods. Okay, that's not true. There actually is a stone-cold formula for the root of a cubic. It's just like a page long, so we don't teach it to students. Questions? No? Okay. All right, so if we have a cubic, we can break it down to the product of a linear times the quadratic. So now I want to shift gears and focus on what can we say about how we factor quadratic polynomials, all right? Let's review that. So, yeah, I'll do that in a second here. So it turns out, it turns out that x squared plus 4x plus 5 cannot be factored using real polynomials. In general, a quadratic polynomial can be factored by the technique of completing the square, but it's always fastest to guess and check or to use, so I say guess and check, or a squared minus b squared is a minus b times a plus b, or a plus b squared equals a squared plus 2ab plus b squared. So these are sort of the three entry-level competitors for completing the square. If I can do one of these three things, I don't really need to complete the square because, it's easier to do one of these three things. So I have three examples illustrating these three things. Okay, so like in class example 1.6.9, we have p of x equal to x squared plus 3x plus 2. One 1.6.10, I have p of x equal to 16x squared minus 9. And in class example 1.6.11, I have p of x equal to x squared plus 6x plus 9. So all three of these, we don't need completing the square. Like we can use basic guess and check factoring, right? It's like how, what's your name again? Fabian. Sorry. Oh, Fabian. Okay. So what do you think about the first one? How would we factor that? I'll do the easy part. Okay, so let's see. We think about 2. Ways to get 2 are like 1 times 2 or minus 1 times minus 2. Since I got a 3 here, and 3 is 1 plus 2, it means I can just put like plus 1 and plus 2. And then so guess and check means we think about how to get the constant term as a multiple of two numbers, write it down, and then multiply it out, see if it worked. So if you multiply this out, you got x squared plus x plus 2x plus 2, which gets us back to there again. So guess and check. This is what we focus the lion's share of our time in like, the pre-calculus class or the intermediate algebra class when we're talking about factoring. Guess and check. This next one, the way I think about it is this is my a squared, and this is my b squared. So what I'm looking at is a squared minus b squared, where a is equal to 4x and b is equal to 3. See, this is equal to 4x squared minus 3 squared, right? And so I can use the difference of squares to factor that. See the difference of squares formula? It's a minus b, a minus b times a plus b, right? So I do 4x minus 3 times 4x plus 3. And there you go. Now, so factored, right? Can we factor further? This is the end of the road, right? Can you factor this further? You could factor out a 4 from both if you wanted. Like you could rewrite this as 4 times 4 times x minus 3/4 times x plus 3/4, right? So if you wanted to, you could do that. So we'd have 16 x minus 3/4 x plus 3/4, right? And so, but if I just say factor completely over the reals, I would be completely fine with this as an answer. However, I would point out, if you want to know where the zeros are of the polynomial, the thing I underlined is to be preferred, because you can immediately see from that in the factor theorem that x equals to plus or minus 3/4 makes p of plus or minus 3/4 0. How about this one? P of what is 0? By the factor theorem, what are the zeros of this one? P of minus 1 is 0. And p of minus 2 is 0, right? So this one here, right? What's that?
X plus 3 times x plus 3.
Right. If you look at it, it actually fits this pattern, right? Where a is equal to 3 and b is, where b is equal to 3 and a is equal to x. Now, if you don't see it as that pattern, that's fine. If you just factored it, that's totally fine. But I'm just saying it is this pattern. That's all I'm saying. And so this is x plus 3 squared, right?
So are you guys using the FOIL?
We always use FOIL. We are always thinking about multiplying out because we always are checking our answer.
It takes me longer, like doing reverse FOIL, than trying to check out if it follows that pattern.
I have no particular preference how you do things as long as you do them correctly and with correct notation, So like, I'm a stickler for notation. If you write things down that are not true, I will take out points. Well, going back to my previous example, do you guys know another way to do it? Like maybe you were taught, remember this thing called synthetic division? if you took pre-calculus here, you're probably taught synthetic division. I know Professor Giles always covers that. I never cover it. I don't believe in synthetic division. I like my division to be real. No, synthetic division is like a cul-de-sac of mathematics. It's really only useful for that kind of algebra. It doesn't really have this kind of long division. It plays out in higher math. There is a notion of division in like other more abstract examples, and basically the way you do it is still long division. This is actually already an example of that, because we teach long division of numbers to start with, right? In like elementary school. 342 divided by 7, by 15, what do? You go, well, that's twice, right? And so that's 30, and so what do you got? You got 42, right? And then so, 2, and then you got 30, and you got 12, and there's your remainder. I mean, that kind of numerical long division, the algorithm for that, it's the same as the algorithm for the polynomial long division, actually, right? So, in contrast, synthetic division is kind of just like, eh. Anyway, what was it Forrest Gump say? Mama said, didn't have anything good to say, don't say anything else, something like that. So that's why I try not to talk about long division, synthetic division. Okay, so you refreshed your memory about basic factoring? So for a quadratic, what are the things that can happen? If we have a quadratic polynomial, how can we think about it? Of course, we have the factor theorem, which I just erased, right? But let me review graphically how we can think about. Actually, let me follow my notes. This is the one bad thing about making fill in the blanks, is I'm married to my notes. Let's see here. Yes. So to complete the story of factoring, I have to introduce complex numbers. So, I mentioned that you cannot factor. Why do you need complex numbers? Well, let me just, before I even define complex numbers, remind you just a very simple, basic example. How about this? X squared plus 1. Can you factor that? But how? So here's how. I mean, I agree with you, but here's how. It's x squared minus I squared. Because I squared isn't equal to -1. So minus I squared is equal to 1. So then I have the difference of squares. I've got a squared minus b squared, so I can go back to my, x minus I, x plus I, right? I shouldn't have erased that factor theorem. I should have left it, and I should have told you, guess what? The factor theorem is still true if we think about complex polynomials. It's just we have to allow for complex inputs. Like it's still this here. So if I have p of x equal to x squared plus 1, then notice that p of I is equal to I squared plus 1, right? Which is 0. And also p of minus I is equal to minus I squared plus 1, which is still equal to minus 1 plus 1, which is 0. So here's your zeros of p of x is x squared plus 1, and here's your factors, right? So the factor theorem still holds for complex numbers. You have a x minus c, where c is a complex number, if and only if, when you evaluate at the complex number, the polynomial gives you 0. The factor theorem extends to complex numbers. All right, but I realize I'm talking about complex numbers as if it's something you know what I'm talking about, right? So let's review what a complex number is. Are you guys need a review of what a complex number is? You say you do? All right, so this is mostly just to, notation, right? So the complex number system is things of the form a plus ib. Here, a and b are real numbers, and I squared is minus 1, right? So you could also say the square root of minus 1 is I, right? So this notation of I in the place of square root of minus 1, it saves us a lot of, like, otherwise we'd have to write square root of minus 1 everywhere, right? And if you look at math, which is like old enough, you'll find just a sea of square root of minus 1s in place of I. But I think Euler introduced the notation I back in the mid-18th century, somewhere in there. All right, so if z is equal to x plus iy, where x and y are real, then the real part of z is equal to x, and the imaginary part of z is equal to y. The real part and the imaginary part are both real numbers. All right? And also the complex conjugate. What's the complex conjugate? Complex conjugate, z bar, is x minus iy. The modulus, or sometimes called the absolute value, you could say, or length, that's what it is. Length of z is like this, and that is equal to the square root of x squared plus y squared. However, there's another way you can write that. ZZ bar is x plus iy times x minus iy. If you multiply that out, what do you get? Z times z bar. You get x times x, which is x squared, right? Notice that you get a plus iyx and a minus iyx. So the yx terms cancel. You get a minus I squared y squared. Say that 5 times fast. Minus I squared y squared. Ugh. Also known as x squared plus y squared. So you see, I could also write the length of a complex number as the square root of the product of the number with its complex conjugate. So I could write this as the square root of ZZ bar. That's another formula for the length of a complex number. All right. And finally, if z is not equal to 0, then the reciprocal, 1 over z, is equal to z bar over zz bar is equal to x minus iy over x squared plus y squared. So this formula shows you this is how to put complex number into Cartesian form. What's the Cartesian form? The Cartesian form of a complex number means you write it in the standard form, like a plus ib or x plus iy. It's the real part plus I times the imaginary part. As I write in your notes, in equation 1.11, that's how you multiply them. And what that equation says is just multiply like usual. You distributive property, you just have to keep track of the fact that I squared is minus 1. But otherwise, we just add and subtract and multiply complex numbers like usual. But there, of course, is some very unusual aspects to it, right? So let's kind of test our mettle here against an example. Let's let z equal 3 plus 2i. And then the question is to find the Cartesian form of z plus 1 over z, I think is what I wrote there. Oh, excuse me, 1 over z plus iz. So let's kind of break it into pieces, right? Let's try the reciprocal part first. How would you do 1 over z? 1 over z, 1 over 3 plus 2i. How do we put that into Cartesian form? Follow the thing right above, right? Remember that thing we did rationalizing, like rational numbers or whatever? So we could take this and multiply by 3 minus 2i, right? So I'm just multiplying by z bar over z bar, multiplying by 1. And that's just what's needed. That does the trick, because that gives us 3 minus 2i divided by what? 9 plus 6i minus 6i. The i's cancel. That's the magic of multiplying by the conjugate. And you see, this just gives us 9 plus 4. So this all multiplies out to 13. See, 3 times 3 is 9. So this right here again is 3 squared plus 6i minus 6i minus 4i squared. That is 13. Because the 6i's cancel, I squared is minus 1, 9 plus 4 is 13. So that's the Cartesian form of 1 over z, right? Iz is easier. What's Iz? Iz is I times 3 plus 2i. How do we do that? Just, that's 3i, right? Plus 2i squared. I squared is minus 1, so we get minus 2 plus 3i. Now the question was to find the Cartesian form of 1 over z plus iz, right? So let's do it. So we've got 3 thirteenths minus 2 thirteenths I plus minus 2 plus 3i. So you guys tell me what's the answer then. Why did I put them both in Cartesian form? Because then I can to add two complex numbers in Cartesian form, we just add the real part to the real part, and we add the imaginary part to the imaginary part, just like that. I can't just add parts unless I have them both in Cartesian form, though. That's one of the advantages of the Cartesian form, is it allows me to actually perform this kind of arithmetic. Now I'm going to have to think. And in terms of how many thirteenths is minus 2? It's minus 26, right? So minus 26 plus 3 is minus 23 over 13. And how many 3 is what? 3 is 39 thirteenths. So I got 39 thirteenths minus 2 thirteenths, 37 thirteenths. Plus I times 37 thirteenths. So there you go. Does that make sense? Now, I'm just doing this as kind of a warm-up to just remind you how we do complex arithmetic, right? We'll actually probably don't need all this for what we're about to do, honestly. But the key observation here, as it connects to polynomial factoring, is just that we can take, with complex numbers, right? We can take a sum of squares and convert it to a difference. That's the trick, right? So this is the main observation. A squared plus b squared, right, is a squared minus ib squared. Because I squared is minus 1, and minus 1 times 1 is 1. So it's a kind of sneaky trick, but we can convert a squared plus b squared to a minus ib times a plus ib. That's the sneaky algebra step, right? So with that in mind, let's factor a couple of these. X squared plus 9, factor that. And this is 1.6.15, just to keep us on track here. Also, see if you can factor 9 times x plus 1 squared plus 16. See if you can now factor these using complex numbers, all right? Oops, sorry. All right. So we do. So you guys help me out. This is x what? Yeah, plus 3i, right? Or minus 3i. And this one, I can do 3 times x plus 1 plus 4i. And 3 times x plus 1 minus 4i. So I'm identifying A is 3 times x plus 1, and B is equal to, 4i. And with that identification, we can look at this as being a squared minus b squared with this and that. So this is kind of an elementary comment, but if you can factor a polynomial one way, can you factor it another way? Like if I could factor a polynomial with real factors, suppose I have a polynomial that factors out to like x plus 1 times x plus 2. Is there any way I could take something of the form, say, x plus 1 times x plus 2 and rewrite it as like x minus, z times x minus z bar? I mean, is there any conceivable way I could somehow, through some sort of algebraic magic, rewrite it so that it's the product of complex factors? The answer is no. All right? The factorization of a polynomial is unique up to like the ordering of the factors. All right? So if you find a way to factor a polynomial, that's sort of its DNA. All right? So what I'm trying to say here is the fact that I've shown that x squared plus 9 can be factored using complex factors, and that this one can be factored using complex factors, that means that it is not possible to factor these using real numbers, right? These are so-called prime or irreducible quadratics. So these guys cannot be factored over the reals. They're so-called irreducible. All right? I think I have been writing. My apologies. My apologies to the people on the YouTube. Oh well. All right. So we need complex numbers. We need complex numbers when certain polynomials, they don't have, we can't factor them with just real numbers, right? We need to use complex numbers to factor those. And so if the factorization is complex, what does that say about the zeros of that polynomial? Well, they're also complex zeros, right? So the factor theorem, if you think about it, it indicates there's no real zero for this either, right? And that's an easier question if you just think about it for a second. Can you solve x squared plus 9 using real numbers equal to 0, you know? Can you solve that? Well, think about it. That is the same as x squared equals to minus 9. Can you find a real number whose square is equal to a negative number? No, this is impossible, right? The solution is empty. There is no real solution to that equation. And that's good because the solutions actually are plus or minus 3i. So that's okay. It's just, you know, it is what it is. Now, so let's talk about completing the square. So here it goes. The quadratic polynomial p of x equal to ax squared plus bx plus c can be rewritten as p of x equals to a times x minus h quantity squared plus k. All right? For h equals to minus b over 2a, and k is equal to p, we'll plug in h. All right. Now that's not actually the technique. This is kind of the result of completing the square. Here's the technique. There are basically two steps. Step one is factor out a. All right. So p of x is a times x squared plus b over a x plus c over a. In order to do that step I just did, what do we need to know about a? I divided by a. What do we have to be able to say? In order to divide by a, I must know that a is non-zero, right? I know a is non-zero because I said it was a quadratic polynomial, right? To say it's quadratic is to say that the coefficient paired to x squared is non-zero, right? So it was hidden in that term. Group terms with x. Okay, so what do I mean by that? We write p of x is equal to a times parentheses x plus b over 2a quantity squared, all right? Now, you guys think about foiling out, if you like, this. What happens if you multiply this out? What's this give you? Multiply that out, you got yourself an x squared plus b over ax plus b squared over 4a squared. If you multiply that out, these are the three terms that you get. Because you get a b over 2ax and another b over 2ax, you add those together, you get b over ax. All right, so if you multiply that out. Now, what do we have to start with? What we have to start with, we have these two terms. Right? So if I trade these two terms for this squared quantity, I have in effect added b squared over 4a squared. I can't just add something without changing the expression, right? So to be fair, I have to subtract that. So I subtract b squared over 4a squared. And then, of course, I have the plus c over a. There you go. That's completing the square. The square is complete at that point. Completing the square is when you take all of the x variable term, and you group it into a square, a single square. There's no linear term. There's just x shifted squared. Now you just have to kind of tilt your head and squint. So you can see that, I'm going to erase this. If you look at that, you can see that the h is equal to minus b over 2a, right? So compare. You can look at this, right? This says h. If I set this equal to, this is equal to a times x minus h quantity squared, right? Plus this thing, right? If I put h equal to minus b over 2a, sorry. I mean, not sorry, but I gotta multiply this through. So plus, goodness gracious. This? H. H is this. Minus b over 2a is h. And I said this was a times x minus h squared plus k. So whatever is left over here, so I multiply this a through, I get c minus b squared over 4a, I guess. I'm multiplying a through that, so this must be, this is the quote-unquote k. Now I said that k was equal to p of h. I guess to be complete in my argument here, I should calculate what is p of h equal to. Shall we try? P of h. In other words, p of minus b over 2a. So that's going to be a times minus b over 2a squared plus b times minus b over 2a plus c. So what does this give us? This gives us b squared over 4a minus b squared over 2a plus c. What's a quarter minus a half? Well, a quarter minus a half is negative a quarter. Ooh, Espanol. I already have a car warranty. Interesting. I don't know. I don't speak Spanish. I'm not sure what they were asking me for. I just assume it was an extended car warranty. It's most of my calls. Anyway, so long story short here, try to get on with it here. Minus b squared over 4a plus c, right? So as you can see, my k is in fact equal to p of h as I said. And for what it's worth, there's a formula for k as well. You take the constant term and you subtract the middle term squared divided by 4 times the leading term. That's kind of nice. That's a formula for the k. What is the significance of h and k graphically? I don't think I have this in the notes, but just so you know, if you put y equals to p of x, right, then that's a parabola, right? The vertex of the parabola is at h comma k. That's the significance of the h and the k, right? So it's like the smallest it gets, or the largest it gets in y is k, and x equals to h is the axis, the axis of symmetry. It divides one the other side of it. And of course, if the parabola looks like this, it's got no real zeros, right? If the parabola looks like this, it's got 2 real zeros, right? If the parabola looks like this, if it bounces, it's got 1 real zero. Those are your 3 choices: no x-intercept, 2 x-intercepts, or 1 x-intercept. That corresponds to irreducible quadratic, can be factored over the real quadratic, factored over the real but repeated quadratic. And of course, you can also turn these upside down, right? These pictures are for a greater than 0, right? If the leading coefficient is less than 0, it turns these pictures upside down, right? And the parabola opens downward instead of upward. All right, now, I just went through I'm almost done here. Let's see here. Yes, let's actually complete the square for some examples, right? So, example. So this is ICE 1.6.17. Here we have x squared plus 2x plus 5. So we do x plus 1 squared, right? That gives me back x squared plus 2x. Now I've added 1, so I just have to subtract 1. There you go. That is completing the square on that. Next, I have like x squared plus 10x plus 25. Now, you probably could just factor that, right? But I'd like to point out to you that we can complete the square. See, we can take x, we take half of 10, which is 5, x plus 5, we square that, right? And then we have to subtract the square of what we added here, so minus 25. Of course, the 25's cancel, and we're just left with x plus 5 squared. So there you go. Completed the square on that one. So completing the square it's really, pretty easy if the leading coefficient is 1. If you have to factor out the a, it's a pain, but you can still do it. It just, let's see here. I give this example as well. I have, x squared minus 6x minus 1. So I complete the square. Now, when I do that, I have to do what? I've just added 9. See, because 3 squared is 9, minus 3 squared is 9. So I have to subtract 9. So I get minus 10 here. At that point, I've completed the square, right? If the question was just to complete the square, in this example was just to complete the square, I'd be done. But I wanted to actually use completing the square to show you how you can factor something that's not obvious to factor, right? Could you guys factor this one? X squared minus 6x minus 1. Could you factor that by guessing and checking? I would argue no. And here's why. I complete the square. Use your imagination. So 10 is actually the square root of 10 squared, right? Now I have difference of squares. So I can go back and fall back on difference of squares algebra. X minus 3 minus the square root of 10. X minus 3 plus the square root of 10. There you go. Factored over the reals. I don't think we would have guessed and checked 3 plus or minus root 10 as the factors, right? When does completing the square work for factoring? Is there any restriction on the technique that I wrote down? You factor out the a, you take the middle term, you divide by 2, you subtract b squared over 4a squared after you group the x's. No, there's no restriction. This is a general technique. We can factor any quadratic using completing the square. And it does not involve any kind of ingenuity. Do you see that? There's no looking at the factorization of numbers and trying to decide what possible pairing of factors works out for the factoring. You just complete the square and use difference of squares. That's the factoring. Like it is a algorithm. It does not require smartness, really. If you learn it, you do it. Guess and check factoring requires a certain amount of being clever. You know, you have to see the numbers to do it. I don't think we emphasize this enough, but completing the square is foolproof method. Foolproof method once you learn it. You can factor any quadratic using completing the square. Now, sometimes the factorizations are complex, right? So here, x squared plus 4x plus 6. So we've got x plus 2 quantity squared, right? I take half of 4 and I square it. So I have to subtract 4 because I just added it. Yep.
Can you explain where you're getting the number you're subtracting?
It is the square. So this time I added 2. So that means I have to subtract 2 squared. 2 squared is 4. So I'm subtracting 4 squared.
So with the one above it, you get 3 squared. Then you added the 1 from, okay.
Yeah.
I got it.
But really, maybe it's helpful to even go back to my technique thing and just get rid of step 1 and just write, let me write it over here. If we have x squared plus bx plus c, we just do x plus b over 2 squared minus b over 2 squared plus c. Like that's more often than not how we complete the square, that pattern. So this one here, which is ICE 1.6.20, I have now got to x plus 2 squared plus 2. When we complete the square and we get square plus a constant, that is signature of the polynomial, the quadratic polynomial being irreducible. That means we can't factor unless we bring in complex numbers. Now, if we bring in complex numbers, how's it go? See, what's that? So this is x plus 2 squared minus 2i squared. Well, square I times the square root of 2, rather. Because I times the square root of 2 squared is minus 2. So minus a minus 2 is plus 2. And then if I do that, I've got difference of squares, and I can now go a minus b, a plus b again, So this factors x plus 2 minus I root 2, x plus 2 plus I times the square root of 2. So cannot be factored over the reals. But everything can be factored into a product of linear factors over the complex numbers, because the complex numbers are what are called algebraically complete. Any polynomial can be factored into a product of linear factors with complex numbers.